Okay, welcome back. This is Mr. Hassan's Maths channel. I'm answering question number 2 from the October-November 2021. This is the Cambridge International A-Level Paper 4 Variant 2, the 9709 syllabus. It's a mechanics paper. It says a van of mass 3,600 kilograms is towing a trailer of mass 1,200 kilograms along a straight horizontal road using a light horizontal rope. There are resistance forces of 700 newtons on the van and 300 newtons on the trailer. The driving force exerted by the fan is 2,500 newtons. Find the tension in the rope. Okay, so as usual, what is important is to make a nice clear diagram to picture the situation. It's always something that helps. Okay, so making a nice clear diagram is what I'm going to do first. So we have a horizontal road. We have a trailer. We have a trailer being pulled along by a van. So here's the trailer and here's the van. They're connected by a tow rope. A bit surprising here, they didn't mention that the rope is inextensible. If they were talking about a rod, then they wouldn't have to mention that, because a rod by definition is inextensible. This is a rope, so really they should mention it's inextensible. They just mention it's light. So a straight horizontal using a light horizontal rope. So light basically means that there's no, we don't consider its mass in our calculations, and the tension all the way through this, the rope is going to be the same all the way through. And really, it should say inextensible, meaning that it doesn't stretch. So all the particles attached to it should have the same acceleration. I think maybe that's a bit of an oversight there. So the van has a mass of 3,600 kilograms. Let me just make that thinner, too thick there. And this has a mass of 1,200 kilograms. Okay, so this is the van, and this is the van, and this is the trailer. Okay, the resistance forces of 700 newtons on the van. Okay, so that's 700 newtons acting this way on the van. Okay, and on the trailer, there are resistance forces of 300 newtons. 300 newtons. Okay, the driving force that is pulling the van is of 2,500 newtons. 2,500 newtons. Okay, so that's everything. So basically, it's accelerating in this direction. Now, the trailer is being pulled forward by the van, and the van is being slowed down by the trailer. So the tensions are acting in this directions in this system. Okay, so we want to find the tension in the rope. So if you want to find the tension in the rope, we need to first find the acceleration. All right, so we have two unknowns here. We have tension and acceleration, both unknown. So what we can do is first we can find the acceleration. And once we found the acceleration, we can then find the tension. So to find the acceleration, we have to eliminate tension from our equation. And we can do that by considering the whole system as one. By considering the whole system as one particle. Whole as one particle. So we can think of it like we have one block moving on this horizontal road, right? And it has a combined mass of 1,200 plus 3,600, that's 4,800 kilograms. And the driving force is 2,500. The driving force is 2,500 newtons. And the total resistance to motion is going to be 700 plus 300, which is 1,000 newtons. So by doing this, we can find what the acceleration is. So now we can find the resultant force on this. So we know that if we resolve the forces in the direction that they're moving, we can say the resultant force is 2,500 minus 1,000, and that's equal to the mass, which is 4,800, times the acceleration. That gives you 1,500 divided by 4,800, and that's the acceleration, which is 15/48. So 15 divided by 48 gives you 5/16, okay, 0.3125 meters per second squared. Okay, now our issue was to find the tension in the rope. Okay, so we know the acceleration of the whole system now. That's now we know is 0.3125. Okay, so the tension in the rope can be found by either considering the particle trailer on its own, okay, or we could consider, if we want to, the van on its own. Okay, both of those will give us the correct value for T. And I'm going to show you both ways because you can see that how it works. It doesn't matter which way you do. But I would, in an exam, I would use the trailer because there's less forces acting on it. Here you have tension, resistance, driving force. Here you just have tension and resistance. So if we consider the trailer on its own, just the trailer, okay, we have the resultant force is the tension minus 1,200. And that's equal to its mass, which is 1,200 times T minus 300, T minus 300, because that's the force acting in the opposite direction, equals the mass, which is 1,200, times the acceleration. The acceleration we know is 0.3125. This is the resultant force equals mass times acceleration. Just like we used here, resultant force equals mass times acceleration. Same thing we're doing here. Resultant force equals mass times acceleration. So T is going to equal 1,200 times 0.3125 plus 300. Okay, so we're going to take this value, multiply it by 1,200, and we're going to add 300 to it. And that gives you 675 newtons. So that's 675 newtons. That is the tension in the rope. And as I said, I'll show you also using the trailer. So we just showed you using the trailer. We'll also show you using the truck. One second. I've just showed you using the trailer. We'll also show you how to do this using the truck and see that we get the same answer. So using the truck, okay, for the truck we have more forces acting. As you can see, we've got 2,500 minus 700 minus T. So 2,500 minus 700 minus T is equal to the mass, and the mass of that is 3,600. Make a bit of space there. So that's 3,600 times acceleration times 0.3125. So we can say here that T is going to be this minus that, because I'm going to add T to both sides and subtract that from both sides. So 2,500 minus 700 is going to be 1,800 minus this 3,600 times 0.3125. Let's see if we get the same answer. Where are we going? There we are. So we get 1,800 minus 3,600 times 0.3125. That gives you exactly the same answer. As you see, 675 newtons. So it doesn't matter which way you use. We use the trailer or the truck, we get the same answer in the end. But I would use the trailer. Why? Because it has less forces acting on it. It's a bit simpler, the calculation. Always look for what makes life easy for you. But both of them should work. You can try to consider the trailer alone, and you can consider the van alone, and it really doesn't matter. And the important thing here is that, you know, people say, oh, when you consider the trailer alone, what about this force, the driving force? Or if you consider the truck alone, what about this resistance force? Well, all of this, the tension in the string, in the rope, that basically kind of like factors for all of those things. If that force was more, the tension would be different. If that force was less, the tension would be different. If the resistant forces here was less or more or changed, that tension will also change. So the tension kind of takes into account all of those things happening outside of the system that affect the system. But when we consider something alone, we only look at the forces acting on that thing by itself. It's very, very important. Okay, so that's part A done. Now for part B, it says the driving force is now removed and the van driver applies a braking force which acts only on the van. The resistant forces remain unchanged. Find the least possible value of the braking force which will cause the rope to become slack. Okay, so now the driving force is now removed and the van driver applies a braking force which acts only on the van. The resistance forces remain unchanged, and we've got to find the least possible value of the braking force which will cause the rope to become slack. Okay, so now the situation before this happens is like this. So this is the situation that we studied above. And what's going to happen now is this is going to go, and this is going to obviously change. That goes. Okay. And you're going to have now an additional force here, braking force, acting in that direction. Okay, this is the braking force acting in that direction. I'll call it B. Okay, the acceleration now will be different now. They want to find the least possible value of the braking force that will cause the rope to become slack. So we want to find it such that the tension in the rope is just become zero. It's just become zero. It's still, you can say it's on the limit of being slack. You can say limiting on being slack. So in that case, the acceleration of the whole system will still be the same. It still has tension in the string. It's about to lose the tension. So we're looking for the limit, the least possible value. Okay, so it's like the limit for it to become slack. Okay, so that's just at the point that it becomes zero. So we're going to consider the tension in the string now to become zero. The tension has become zero in the string. Okay, in the rope, just becomes zero. So we want to find the least possible value. So if the tension has become zero and the rope is still it's still taut, you could say, it hasn't quite become slack yet, then both particles will still be moving with the same acceleration. So we want to find that braking force will cause them to still be moving with the same acceleration, okay, before the string becomes slack. Okay, just enough to keep the string from becoming slack. So it's like limiting equilibrium almost, you could say, like when you have a situation with the friction and it's just about to slide. This is just about to become slack, but it's not quite slack. They're still moving with the same acceleration. And that's how you can think about it. So therefore we can consider these two particles separately. So let's look at the force on the van and look at the forces on the trailer. So now when this has become zero and this has become zero, for the van it's moving in this direction. So if we resolve the forces, you've got minus B minus 700 is equal to its mass, which is 3,600 times the acceleration. Okay, and we can see for the trailer, it's going this direction as well. So we can see the only forces acting on this trailer are minus 300, and that's equal to its mass, which is 1,200 times its acceleration. Okay, so we have these equations which we can solve. So we say A is equal to, that's going to be minus 300 over 1,200, and we can substitute that into this equation here. Okay, so like this is equation 1 and equation 2. If we substitute this into that equation, we have a bit of space here, we can say we want to find the mean, so we can say minus B, okay, minus 700 is equal to 3,600 times minus 300 over 1,200. Okay, they cancel out. That gives you 3. So you got minus b minus 700 is equal to minus 900. So you can say minus 700 plus 900 is equal to b. So b is going to be 200 newtons. Okay, so basically, it's a bit of a strange one here, but it's like in limiting tension being in the string. So the string is still, not slack, okay, but there's no tension in it. The tension is 0. We're looking at the limit of it being, so basically that will occur when the acceleration of the two particles is still the same. So the string is not slack. If the string is slack, then the acceleration of the two particles will not be the same. But here we're finding the value such that the string is slack at its limit. Sorry, the string is taut at its limit. It's just about to become slack. If you put the brake anymore, it will become slack. Okay, so it's still not slack. So the objects are still moving with a constant acceleration, the same acceleration, but the tension in the string is 0. So it's a bit of a strange one, but I hope you understood. So the answer was 200 newtons. Thank you for watching. Other questions from this particular paper can be found in the playlist on the top right of the screen at the end of this video. Other questions from the topic of connected particles, you can find it in the playlist over here. You can subscribe to my channel by clicking on this link, and the link here will take you to a video which shows you how to use my channel effectively. Thank you for watching and see you soon.